Welcome to the last video for this second week of courses. We're going to be covering two topics: convolutions of functions and the Dirac delta function. Let's first go into convolutions. It's a new operator that we want to introduce, and the idea is that it takes two functions and combine them in some ways. In a very similar way as like a sum of two functions or the product of two functions can work. But it combines them by taking the integral of them with one of them being shifted. So the convolution of f and g computed at t is the integral between 0 and t of f tau g t minus tau d tau. Tau is a dummy variable, so you can choose any name for it. We are introducing them because they happen to work very smoothly with integration kernels. And in particular, for our personal goal, they work very well with the Laplace transformation. So let's look at Laplace transform of convolutions. By definition, we can write it as the integral from 0 to infinity of the convolution of f and g times the exponential of minus st. So let's write explicitly what the convolution is. So expand into a new integral in the center. And we would like to change the order of the integration. So in general, when we're integrating over two variables, we can swap the order of integration if the two bounds of the integrals don't depend on each other. If they do depend on each other, we have to be a bit more careful because the ratio needs to be always the same. We have to keep track of the integration domain. So let's look at the integration domain. In the plane t tau, we have that t goes from 0 to infinity, and tau in the vertical direction goes from 0 to a finite value, t in particular. So it stops at a certain line that is tau equals to t. This one here, the area shaded between tau equals to 0 and tau equals to t, it's the integration domain that we want to maintain. If we are to swap the order of the integration, then we need to be careful to always span the same integration domain. So we need to have that the integral in which tau was going from 0 to t and t was going from 0 to infinity is now changing, being t goes from tau to infinity. So we're going horizontally in t always, and tau is going from 0 to infinity. So keeping this change of the integration order in mind, if we want to change the order of tau and t in our Laplace transform of the convolution, then this is what we retrieve. We haven't changed anything in the center formula. We have just exchanged the order in which dt and d tau happen and the order of the two integrals. Now we want to look at the center integral, the one that goes from tau to infinity in dt. Here we have t minus tau. We don't like that. We redefine t minus tau to be mu. So dt doesn't change. dt is equal to d mu. But t was ranging from tau to infinity. Mu has shifted everything down by tau, so mu goes from 0 to infinity. So this is our new equation. We like it because now there is f of tau and g of mu. There is also the exponential of minus s times mu plus tau. And if we remember our exponential correctly, this is actually the product of the exponential of minus s mu and the exponential minus s tau. Isn't this great? Now we have a block that only depends on tau, a block that only depends on mu, so we can easily split these two integrals, having one of it only depending on tau, going from 0 to infinity, and one of them only depending on mu, going from 0 to infinity. So recapitulating what we have done, we have taken the Laplace transform of the convolution, we have written it explicitly, we have done some remanaging of the variables inside, and have been perfectly able to split it into two integrals that happen to be actually the Laplace transform of f and the Laplace transform of g. The fact that they are depending on mu and tau or any other doesn't really matter. They're dummy variables. We can call them however we want. To apply this, we would like to prove that f star g, so the convolution of f and g, is equal to the convolution of g and f. If we use our application, well, we know that the Laplace transform of f convoluted g is equal to the product of the two Laplace transforms. We know that products are invertible, so we invert the two products, and this is the Laplace transform of g convoluted f. This needs still a little bit to prove that the two elements inside the Laplace transform are actually the same. What it needs is that we're actually assuming the Laplace transform to be invertible. I haven't proven it yet, but we will see next week that that is indeed true. If we want to prove the same statement, so that the convolution of fg is the same as the convolution of g and f, then we have to go through their integral. So if you write just the definition of the convolution, then we can do a very similar change of what variable as we did before. We're going to introduce mu as t minus tau. And now the integral inside is respect to d tau. So d mu is actually equal to minus d tau. Also, if we do the computations, when tau is equal to 0, mu is equal to t, and when tau is equal to t, mu is equal to 0. So practically, we have swapped around the bounds of the integral. Then we write everything down. Tau becomes t minus mu, t minus tau becomes mu, and d tau becomes minus d mu. And now we have a negative integral given by the minus d mu of something that has the bounds of the integration bounds swapped. We can actually swap them back and retrieve something that is indeed the convolution of g times f. Other properties of convolutions. It's associative. That means that you can associate, if you have a convolution of multiple things, you can do any convolution first and then the others later, and you will have the same result. It's distributive. So the convolution of a sum is the sum of the two convolutions. These two elements are enough to tell us that the convolution is a linear operator. On top of that, we have that the convolution of 0 is actually 0. So now that we have finished looking into convolutions, let's look at a new function, the Dirac's delta. Why am I so careful in saying function? Because technically the Dirac delta, also called the delta function, is not a function. So it's usually defined by delta of t minus t0, and it's something that is 0 everywhere except at t0. The formal definition is that the integral from minus infinity to plus infinity of delta t minus t0 of any function, I write it as phi t because this is the usual notation, but that is any function that you can think of, is actually the evaluation of that function at t0. So we kind of are thinking about delta being a spike at t0 that has area equal to 1. So it's something that has no width, but still a non-zero area. We kind of say that the delta function evaluated at t0 is infinity, but still that integral that I just stated, if we just consider the delta function as being a function, that integral makes no sense. For this reason, the delta function is not a function per se, it's a generalized function or a distribution. I don't expect you to know a lot about either of these terms. I just want to explain what the delta function is. So let's try to look at how to view it. So here I have drawn on the left this delta h. Delta h is something that is around t0, and if you're close enough to t0 is non-zero, if you're too far is 0. So if you're further away than h from t0, dh is 0. If you're close enough, it still needs to have an area of 1, so it's height is 1 over 2h. When h, that is the width of your dh, is going to 0, delta h is tending to delta. And what is happening is that you're restricting this rectangle and having it higher and higher until it just disappears. It's this spike that still has area 1 because that's how you built it. If we, there is a small typo in the slides, it's delta h. If we take the limit for h tending to infinity of the integral we saw before going from minus infinity to plus infinity of delta h times phi t, we call them test functions, any type of function in there. Then we see that it indeed converges to being the value of phi at time 0, at t0. So it does correspond to what we defined before. We can also view it as the limit of a Gaussian function around t0 for sigma going to 0. It's the same idea that the Gaussian function has, by definition, an integral of 1, and when you're taking the limit for s to sigma going to infinity, you're kind of squishing that area all on top of only t0. Another way of looking at it is looking at the Heaviside function. The Heaviside function is defined to be 0 anywhere before t0 and 1 everywhere after t1. Obviously, we usually think about it as having a discontinuity that we just cannot jump. But formally, we can state that the Dirac delta is the derivative of the Heaviside function. Fun fact, I always thought that the Heaviside function was called like that because it had a side that was heavier than the other, but it's actually had been found by a mathematician called Heaviside. So let's look at the Laplace transform of the Dirac's delta. I mean, I spent some time talking about it. It must be quite important. It's also the last special Laplace transform that we're going to be looking at. So we just write it down as the formal definition of the Laplace transform is the integral between 0 and infinity of the Dirac's delta times our exponential of minus st. And now for the property of the delta function that we have just seen, this really simplifies into being the exponential of minus s times the t0 that we have chosen for our Dirac's delta.